The inverse of a matrix M, denoted M inverse, is, or rather, I should say the inverse of a square matrix M, denoted M inverse, is the matrix such that M inverse is the identity matrix and M inverse M is also the identity matrix. So sometimes it's possible that there might be a matrix, especially not for square matrices, there might be a matrix which satisfies one of these two equations but not the other one. Because as we know, it's not always true that M inverse is M inverse M. So that's why we need both of these. So this is just the definition of the inverse matrix, but how do we find it? So one by one case, which we're never going to be interested in. If we have a matrix X, the inverse of that is this if X is non-zero. So for example, the inverse of the matrix 5 would be 1/5, which I think is quite kind of obvious. Important note before we go any further is that M is invertible, and that just means the inverse exists, if and only if M is non-singular. What does non-singular mean? It means the determinant, this means determinant of M is non-zero. If the determinant's 0, the inverse does not exist. So that's an important thing to be aware of. Okay, 2 by 2 case. So if M equals ABCD is non-singular, meaning determinant is non-zero, M inverse is given by the formula 1 over det M, and then we swap the entries A and D, and we negate the other two entries. So this is an important formula, and we'll prove it a bit later. We will prove it, but not just yet. Yeah, and we've observed this doesn't exist if the determinant of M is 0, because we can't divide by 0. So let's see a quick example. If we have the matrix, let's say 1, 2, minus 4, 7, let's find the inverse of this. Well, it's 1 over the determinant, so that's 1 over 1 times 7 minus 2 times minus 4, and then we swap A and D, and we negate the other two entries. So this is, well, 7 plus 8 is 15. So this is 1/15 of this matrix, which is 7/15 minus 2/15, 4/15, 1/15. And you can easily check this is right if you want by multiplying together these two, because we know we'd expect then to get the identity matrix, I2, which is 1, 0, 0, 1. And same if we multiplied them the other way around. Your calculator can do this, so in general, no need to do it by hand unless one of the entries is algebraic. Then you must do it like this, because you have no other way to do it. And, okay, now let's prove this formula in the red box. So, what do we want to show? Well, if M is the inverse, we need to show that M inverse is the identity matrix, and same for the other way around. I think I'll only do one way around, I won't do both of them. Let's do M inverse. So we're going to check that this does give us, I mean, really, we shouldn't call this M inverse just yet until we know it's the inverse, but we need to check if we do this and then multiply by this, that it does give us the identity matrix. Notice the determinant, 1 over the determinant is a constant, so I can bring that to the front. And then I need to multiply together these two matrices. So the answer is going to be a 2 by 2 matrix. In the top left entry, First row, first column, I'm going to have AD minus BC. First row, second column, I'm going to have minus AB plus AB. From this times this, and then this B times this A. Second row, first column, I'm going to have CD minus DC. And second row, second column, I'm going to have minus BC plus AD. And then this simplifies to AD minus BC, 0, 0, AD minus BC. And then if we times by 1 over the determinant at the front, we get the matrix 1, 0, 0, 1, which is the identity matrix. And then we just have to do the same thing the other way around, which will give us the same answer, and that's the end of the proof. And one other result we'll prove, so I'll call this a proposition. It's just kind of a small result that's useful. If A and B are non-singular, and AB is defined, then we have that AB inverse is B inverse A inverse. Okay, so let's prove this formula. And by the way, it's also true that the determinant of AB, we won't prove that now, but just so you know, the determinant of AB is the determinant of A times the determinant of B. But we don't need this in this particular proof. This is just another result that it reminded me of. Okay, so let's do the proof then. So, since A and B are non-singular, A inverse and B inverse exist. We want to show the inverse of AB is given by this. So let's check. Let's do AB times this and see if we get the identity, and then we'll do the same thing the other way around. So AB times this, well, remember, matrix multiplication is associative. The order of brackets doesn't matter, so I can change the order of the brackets like this. And then since B inverse is the inverse of B, this is IN in the middle, the identity matrix. And then multiplying something by the identity matrix doesn't change it. So this is just A inverse, which again is the identity matrix. And then if we do it the other way around, we can again, because matrix multiplication is associative, change the order of the brackets. And then in the middle here, A inverse A, that's the identity matrix. And then B inverse times the identity matrix is just B inverse again. And then B inverse B is the identity matrix. So we're done. So therefore, the inverse of AB must be this guy, B inverse A inverse. Because regardless of which order we multiplied in, we got the identity. So we've proved this formula. End of proof.